So welcome back for the third lecture of week 1. So in this lecture and the next lecture, I'll discuss about one very important concept from classical NLP that has gone on to deep models, also the large language models, and that is N-gram language models. So we will do this in 2 parts, lecture 3 and lecture 4. So what are we covering in this lecture? So we'll talk about what is language modeling, and as I mentioned, language modeling, we typically call them LMs, and this is the LM in the large language models, so LLMs. So we'll talk about the language modeling, and this idea came from classical NLP itself. So we will discuss that in detail this lecture and the next. So we'll talk about what are N-gram language models and certain practical issues with them in this lecture. So let's give some intuition why this language modeling is actually needed. What does it actually do? So consider the task of predicting the next word. So your sentences, the water of Walden Pond is beautifully, right? And you have to predict what is the next word that will come after this. So is it blue, green, clear? Is it refrigerator, that, right? So typically if you say about water, you will say beautifully blue, right? You will typically select blue. But can a language model also tell, can an automated model also tell which one is the correct word, right, after the sequence of words? So this is what we mean by language models, a system that can predict the upcoming word. So that means if you have multiple possibilities, it can assign a probability to each potential next word. So suppose you have a finite set of vocabulary, right, as we discussed, you have a finite set of words that can come next. So you can assign a probability to each word, and by this method it can also assign a probability to the whole sentence. So if you have multiple sentences competing for various applications, you can find out probability that which sentence has a higher probability, and you can accordingly select. Okay, so it can do both the tasks, probability to each potential next word and to the whole sentence. Now why word prediction or this language modeling is important? So it's helpful part for many language tasks. So think about you are doing grammar or spell checking. So suppose this is the sentence that is given to you. Now you want to say, okay, there are multiple ways you can correct this sentence. One is this there is wrong and it should be there. So understand that this there itself is a correct word. It's a correct word in isolation. But in this context, this is not the correct word. So you should have this particular spelling of there, right? So this is called context sensitive spelling correction task. So where language models are very helpful, because you can try out all possible variations and see which sentence as a whole has a higher probability. So you'll find out this sentence should have a higher probability than the previous sentence. Okay. So if they are A, B, I should have probability of B should be higher than probability of A. Same in the next sentence, everything has improved, and you would correct it to everything has improved. Okay. Another task like speech recognition, where you are hearing an audio and you have to transcribe it to text. What is the corresponding sentence that is spoken? So like given a text, it may be I'll be back soonish, right? But the way the person is speaking, you may also hear something like I will be soonish, right? I mean, but the second one does not make sense, and we will never think about this possibility. But language models, or I mean, the ASR models can possibly give you this output, the second output. Then you can use language modeling to say, okay, this sentence S1, this sentence S2, and probability of S1 is higher than probability S2. So if my ASR model is giving output for both the sentences, I would choose S1 and not S2. And yeah, I mean, this is how the large language models work. So language, as I said, large language models has this suffix language models, right? So large language models are trained to predict the next word. So, and that's why we will see they are called autoregressive models. So they will predict one word at a time. So, and that's how their training also happens. So they are all pre-trained based on the next word prediction task. So language modeling is a very crucial concept in understanding large language models. And large language models are trained with this objective, and also they generate by predicting the next word. Right? So you will, every time given the previous prompt and the current generated output, they will predict the next word. And this they keep on doing, right, until they achieve the final end of sentence or end of output. Okay, so they will keep on predicting the next word over and over again. So language modeling is a very, very crucial concept. Now, even you think about the paradigms that we have, right, the way we interact with deep learning models, large language models. So first one would be a pre-training phase where you pre-train the model to obtain a very good initialization of weights, and then you do supervised fine tuning by which you can make it work for a certain task like sentiment classification or named entity recognition, right. So the first step, this is the pre-training step, and this requires language modeling. So this is a pre-training step, and this is based on self-supervision, right. We will talk about these concepts in detail. So this is one way, this is one of the way in which you can interact with the large models. Another way is you have done unsupervised pre-training, and then you can prompt them. So there you're not modifying the parameters, but you are using prompting to actually generate some output from the models. And prompt can have task description, examples, and the actual task that you want to do. Right? Like here you are giving this task description that you want to translate English to French, you are giving some examples, and then you have the particular phrase that you want to translate. Right? But the first step before using prompting is you have to do pre-training, unsupervised pre-training. And this whole thing requires language modeling. So the way we do pre-training is based on language modeling objective. So language modeling forms the core of most self-supervised NLP approaches, and that's why this is very, very crucial. Okay. Now, given this motivation of language models in the current context, let's study this more formally, right? More so in the classical NLP way. So what is the objective of language modeling? So you are trying to find the probability of a sequence of words. So you have the sequence of words W1, W2 up to Wn, and let's say W is the overall sentence. You want to find the probability of the sentence W. A related task that you would also be able to do is probability of an upcoming word given the previous sequence. W1, W2, W3 are given to you. You want to predict what is the probability for the word W4. So any model that does any of this is called a language model. Okay. And typically language models will do both the tasks. So how? Because the way you compute PW and the way you compute this are actually connected. Yes. So how do you compute the joint probability of the entire sequence, probability of sequence W? So let's take an example. So this was the example that we had taken earlier. The water of Waldell Pond is so beautifully blue. I want to find the probability of this whole sentence. So how will we do that? We rely on the chain rule of probability. Okay. So what is the chain rule of probability? So you may recall the conditional probability definition. So you will say, okay, probability of an event B given in another event A is the joint probability divided by probability A, right? So this is how you compute the conditional probabilities, B given A. Now if you rewrite this, you can say probability of joint event AB is PA times PB given A, right? And this becomes the chain rule of probability. So now suppose you have more variables like A, B, C, D it's okay. I can write probability of A, probability of B given A, C given AB, D given ABC, right, just by using this chain rule. In general, if I have n variables x1 to xn, I can say probability of x1, x2 given x1, x3 given the previous ones, xn given the previous n minus 1 variables. Right? That is my chain rule of probability. Now, how do I use that to find the probability of a sentence or a sequence of words? So that means if I am given n words, say this is the notation I use, w1 to n, word 1 to word n, I will find the probability by probability of w1, w2 given w1 and so on, wn given word 1 to n minus 1, right. So, yeah, so each word given the previous words, right, in the sequence. So now apply it for the sentence that we have. So the water of Walden Pond is so beautifully blue. I will say the probability of the sequence is probability of water given the, of given the water, Walden given the water of, pond given the water of Walden, and I keep on multiplying probability is given everything else, probability so given everything else before, probability beautifully given everything else before, probability blue given everything else before. Right. And this will give me the entire probability of the sentence just by applying chain rule of probability, no other assumption. Okay. Now, the question is how would we estimate these probabilities? Right. So the probability blue given the water of Walden Pond is so beautifully, right, the word blue comes after that, would be the number of times I have seen this entire span, and suppose I have seen this 100 times, and then how many times I have seen this followed by blue, right. And this I would have seen lesser times, right, because I have anyway seen the previous thing there. So let's say I have seen this 20 times. So I will say, okay, the count of the water of Walden Pond is so beautifully blue divided by the count of the water of Walden Pond is so beautifully, right, and it will be 20 by 100, 0.2 probability, right. Okay, that's how I'll compute it. The problem that you can see immediately is that, okay, this is a very long phrase, and how often would I have even seen this whole phrase in the data? Like, how will I find the count of the water of Walden Pond is so beautifully blue? It may have been the only occurrence in the whole data set for which I am trying to find the probability of this, right. So I may have never seen enough data for estimating these, right. That becomes one of the crucial problems with language models. So that's where we go to certain assumptions. We say, okay, we cannot directly compute all these probability that we were seeing here. So we cannot compute all of these probabilities. So you have to make some assumption, right? And the assumption that we make is the Markov assumption. So what is that? So it says, for example, to compute probability of blue given the previous sequence, I can just use the last word that I have seen in the sequence. So probability approximated by probability blue given beautifully, right. So in general, probability of nth word given the previous n minus 1th word can be approximated by probability of w1 given just the last word n minus 1, right. That is one particular assumption. It's called bigram assumption. First order Markov model. But you can also change the order. You can say I will use the 0th order Markov model, first order, second order, and so on. So this is the whole idea. So you would approximate it by just the previous few words that you have seen in the sequence. Okay, so this is the bigram assumption. So you are saying wk given wk minus 1. So instead of taking the previous k minus 1 words, you are just taking the k minus 1th word, right. So this is k minus 1 previous words. This is just one word, right. So this is the assumption that you are making. So we approximate each component in the product, right. So if I have this product wn given the previous nth words, I will say, okay, if I am using in general, I will say wn given the words from n minus n plus 1 up to n minus 1, right. So wn given w this up to w of n minus 1, right. So how many previous words I am using? So I am using n minus 1 to n minus 1, right. So I am using n minus 1 previous words, right. So Wn given n minus 1 previous words, and this is called an N-gram language model. N-gram language model makes the assumption that the probability of the current word depends on only the previous n minus 1 words. Okay, and you can use n is equal to 1, so it becomes a unigram language model. So that means it will not depend on anything. You will just find the probability of the word itself. If you use n is equal to 2, it's called a bigram language model. So probability depending on just the previous word. N is equal to 3, it becomes a trigram language model. It depends on the previous 2 words, and so on. Okay. So like unigram language model. So this is very easy. So you will approximate the probability of the sequence by multiplying the probability of the individual words. Probability of W1 times probability of W2 up to probability of Wn. And this is an example of what will happen if you just use this to generate some sentences, right? Because you have no conditioning on previous words, it's like generating each word independently. So you see to him, swallowed, confess, here, both, which, I mean they are like random words spread, right? This does not make much sense. So even the 2 consecutive words do not make much sense, right? So this is just like random words. So the unigram language model is okay, but it's not good for generation because it cannot use any context, any previous context. Now what is bigram language model? So you will approximate Wi given the previous I minus 1 words as Wi given just the Wi minus 1. Okay. And if you try to use bigram language model to generate sentences, so you see, okay, at least you will feel some sanity in the 2 words together, like what means I confess, all sorts, he is, right, would seem, last December, right. But if you see read the sentence, last December through the way to preserve the Hudson Corporation, and it does not make any sense. But at least 2 words together, they have some connection, and so on. So we will come to some examples even later on. Yeah, so this is an example of approximating Shakespeare. So you take the entire Shakespeare data and learn these language models, unigram, bigram, trigram, quadgram, and you try to see what generation comes out. So if you learn, they would actually emit words from the vocabulary of Shakespeare, right? So even for unigram, you will see the kind of words that were used, right? Excellency and knave, interesting words, right? But just the words, the phrases do not make much sense. If you go to bigram, right, this is what we have seen, I confess, then all sorts, right? If you go to trigram, it starts making a little bit more sense, sweet prince, first of shall die, Harry off, and so on, a very good friend. And if you go to quadgram, so yes, now the sentences themselves will start making some sense, right? It cannot be but so, indeed the short and the long. I mean, why you not tell me who I am? So at least they make some sense, right? So that's how if you go from unigram, bigram, trigram, quadgram, they become better and better model of text. Okay. Now, what are the problems with N-gram language models? They can't handle long distance dependencies, because you see we talk about unigram, bigram, trigram, quadgram, and in general in language you cannot say that a word will depend only on the previous 3 words or 4 words. Like take this example, the soups that I made from the new cookbook I bought yesterday were amazingly delicious, right? And the word were, it depends on the soups, right? If you made it depend on the cookbook, then you will say was, right, not were. So it has to depend on the soups, and that is like many words before. There are many words in between, right? So you have to use 10 or 11 gram language model. But as you keep on increasing this n in n-gram language model, so it becomes more and more difficult to estimate the probabilities, right? Because you may not have seen enough data, and you also have a lot of parameters to estimate, right, in general. So like in unigram, you have only the parameters are this is the probability of individual word, and there are v words, right, only v parameters that you have to estimate. But once you go to bigram language model, there is probability wi given wj, and then that means all possible pairs. So it may be v square in theory, but in practice they are little less, but in theory they can be square parameters that you have to learn, right? And it keeps on increasing exponentially. For 4 gram, this will be v to the power 4, that many parameters. Right? So yeah, I mean, so this is a problem with N-gram language models, and large language models typically offer the solution because they can handle much larger context, because they use the embedding spaces, and they can model synonymy. Like if you have learned something for probability of a word given, I went to play cricket, and there is a word after that. If you replace any of the word with a synonym, this will not hold, right? So instead of I, if I replace it by something similar like we and all, the probability that you have learned will not be applicable. But if you use embedding spaces, we will see that it actually generalizes to synonyms. So two problems: one's generalizing to synonyms, and second handling larger context. That is taken care of by the large language models. Okay. But then why we are studying N-gram language models? So even if they don't solve these problems, they are a very nice clear paradigm. It will help us introduce many important issues that will be helpful later on, like what is the training and test set that you would use, perplexity as a metric, and how do you sample and generate sentences, and we will see ideas like interpolation and backoff. Okay. So let's quickly see how do we estimate the N-gram probabilities. So suppose I am using the bigram model. So we use the MLE estimate, maximum likelihood estimate. So idea is that we want to find the values that will make the probability of observation, right? The observed data will become the most probable. Right? So if you use that, probability of a word wi given wi minus 1 is nothing but the number of times wi minus 1 followed by wi occurs in the data divided by the number of times only wi minus 1 occurs in the data. Right? I mean, it's the short form. So just a simple example. Suppose in a corpus you have probability of paper given question as 0.3, right? Paper coming after question is 0.3, and the number of times the word question occurs is 600. What is the frequency of the pair question paper in the corpus C, right? So can you find this? So probability paper given question is number of times you have question followed by paper divided by number of times you have question, and what is given? 0.3 is equal to x, we don't know the pair frequency, divided by 600. So x is 180. So this is 180 times. Right? This is a simple example. Frequency is 180. Okay. Another example, let's say we have 3 sentences. So start of sentence: I am here, who am I? I would like to know. I want to compute some bigram probabilities, like I given start of sentence. So I will say divide by number of times start of sentence occurs 3, and how many times start of sentence followed by I occurs. So 1, 2, 2 by 3. Like that, end of sentence given here. So here occurs only 1 times, and here followed by end of sentence occurs also 1 times. So like that you can compute the other probabilities that are given in the slide, right, just for practice. And you can use this to compute the probability of the entire sentence. So suppose my sentence is probability sentence is start of sentence, I want English food. So I'll compute it by, in a bigram language model, I given start of sentence, want given I, English given want, and so on up to I go to end of sentence given food. And I'll have individual bigram probabilities, I'll multiply them, right. Now immediately you may see an issue, right. I mean, even after this approximation, if you have a long sentence, you're multiplying multiple probabilities, and what can happen? If you're multiplying probability values, every value is less than 1, so it may actually underflow, it may become less than the minimum precision of the system, and it will turn out to be 0, although it is non-zero, right, very small number. So because finally we may not be interested in the actual, so we may be interested only in the comparison. So what we do, we take it to the log space. Log space, what happens? Multiplication of probability is nothing but addition of log probabilities. So what we get are the log probability, addition of log probabilities, right? And typically we work with addition of log probabilities rather than multiplication of probabilities. So that is one practical issue. Okay. So yeah, I mean, with that I'll end this particular lecture. So we will continue on this in the next lecture about N-gram language models. You can read the chapter 3 of our SLP book to get more idea about this topic.